Hi, everybody. I am Katherine Gallagher. As Alex said, I am from the MIT Quest for Intelligence, where I do work on a variety of machine learning projects. So everything from sports to medicine and all sorts of other applications. This one happens to be about sports. And I would like to start off by saying that the title is a long and complicated way of basically saying we're going to look at the way that athletes move and see what we can learn from it. So before we get into why we're doing that, I'm just going to show you what our pipeline looks like. And the reason I'm going to do this, I'm going to start off, is because this is actually going to be largely a love letter to Google Cloud Platform. And what you can see here is what we're doing is we're taking some videos, unlabeled videos, and we're going to put them through this pipeline. And what we're going to end up with is an identification of the player viewed in the video. And the way that we actually prep those videos to go into the machine learning models that tell us who the player is by starting off by, let's just do some video processing. So one of the major advancements in recent years in basically all of sports is now we have the ability to not just capture a lot of data, like filming your soccer matches or football matches if you're, talking about the UK and using sensitive language, or football, American football, whatever it is, we televise almost all of our matches. We have a lot of broadcast video. But until recently, you couldn't do all that much from it. And this is a first step in trying to see, without having a human in the loop, hand labeling the video, as do a lot of the analysis software people you might hire if you want to track your players during a game. During practice, you might have them wear GPS sensors. During a game, you can't do that. So a lot of people spend a lot of time going in and using a computer program to actually manually label where these players are at any given time. Can we actually just automate that? And moreover, in the automation process, can we learn anything more about what the players are actually doing while they're on the field, maybe collect some stats about their movement and how that might correlate to performance? So starting off with just some raw video, and this demo, I use just publicly available tennis matches that I scraped from the YouTube Wimbledon account. Thank you, YouTube Wimbledon account. We did also do work with soccer videos and basketball videos, but I'm unfortunately not allowed to display those, so tennis it is. Starting off at the very first thing you're seeing here with the Google Video Intelligence API, taking these tennis videos off of Wimbledon. They're broadcasts. These are not special cameras that were set up in the stadium with the purpose of tracking the players. They are simply to show a televised tennis match to a large global audience. And therefore, you get shots in these matches that are just audience shots. You get the players, after a volley, drinking water, talking to their coaches. So the very first thing we want to do is clean that up. And Google Video Intelligence API, really fantastic, offers the option of doing some automated shot change detection, which means I can run my videos through that and get out the timestamps every time a continuous shot moves to the next continuous shot. I can then use those timestamps to clip the videos at those shots and only extract the shots that I'm interested in, which, as you can see all the way on the left-hand side here, that is left, right? Super dyslexic, sorry. Yeah, left. All the way on the left-hand side here are just the full court where you can see both players. And then in order to make it fair, I am only ever going to look at the bottom half of the court where the player is obviously somewhat larger because they're closer, and so that there's no sort of variance in who gets more time on which side of the court when, which will become relevant later. So we're only going to look at the bottom half of the court, and again, that's the second part of this video processing pipeline, where you're selecting just the action clips and cropping to the bottom half. So now we've got a whole bunch of clips of the player nearest to the camera, and The nice thing about tennis is that it's fairly easy then to only track that one player. The Google Video Intelligence API now offers automated tracking, which would have been super nice if that was available when I was doing this. Story of my life, apparently, with the Google developments. It's nice that they're out now, so the rest of you don't have to suffer the way I did. But what I actually had to do was do some basic object detection on these players to identify where the players were. Again, great for tennis, not so fun for a soccer match where you've got X number of players on the field and in the camera at any given time, and you're trying to identify them all and then extract their coordinates on the screen so that you can then apply a bounding box to them and crop from there. Don't do that. Use the Google Video Intelligence API tracking, or rather the Video AutoML tracking. So you've got these videos, though, and they only contain that one player, each of them that you're interested in. Whether it's for tennis or for soccer, each of these videos now that you have is just of that one player. We're then going to feed that into pose extraction, which you saw with Ramsey. They now have, again, Google API will soon offer that, or Google Cloud Platform will soon offer that. I used CMU's OpenPose, which was also great. And I did find when playing around with some other pose extraction programs that it really did not matter which one I was using. The accuracy was pretty much the same for, I think I tried 4. So kind of stuck with OpenPose because it was the easiest to use. And this is all happening, I should mention, on Cloud Engine or Compute Engine on the cloud. So this is all going on VMs that are portioned with GPUs to speed up the whole video processing thing, because that's pretty computationally expensive. And what the pose extraction is doing, as you saw in Ramsey's presentation, is just showing us what that skeleton looks like for the players. So here's just a GIF of CMU's OpenPose working on a video of soccer players, and you can see it's extracting all of their little skeletons and superimposing that on the video so you have a nice visual. Finally, we're going to take all of those skeletons and we're going to shove those through a machine learning model, and the machine learning model is going to output what it thinks, who it thinks that player is. So the rest of the time, I'm going to be talking about pose. I'd like you to think about why this is actually interesting. One is obviously, can we automate player identification? Wouldn't it be nice if we didn't have to have humans labeling those videos to say, this is player 1, this is player 2, et cetera, especially, again, if you're working in soccer where there's a whole lot of players you care about, and rather just have this automated for you. It can also collect and augment data about performance. So when you're not just saying this is player 1, this is player 2, but rather you have that player's skeleton, we know from previous studies about gait recognition that the way that you move as an individual is fairly unique to you. And so we can, A, yes, maybe identify you, but B, we can learn things about how the way that you move when you play your sport affects your performance in your sport. And so we've been talking a lot about team sports, but what about something like diving? How did the way that you approached a particular dive affect the score that you received on your dive? How did the way that you swung your golf club affect how far the ball went? And of course, again, for team sports, it's pretty easy to see, goal correlation or how the team performed overall. If they had particular configurations of players that move in a certain way. There's also some additional studies we're talking about later where even just the direction of the gaze that the player has before they make a pass might matter. And we can collect that just from the skeletal extraction because you can tell where the player's nose is, and that is an okay proxy for gaze, it seems. So you can make recommendations on how to improve your performance. The other thing is, unlike traditional object detection where you're just kind of looking at a picture of the player, the skeletons are robust to variance in lighting or clothing if you train on a bunch of home games because that's the data you have, and then you want to predict the identities of players in away games and they're wearing different color uniforms. That can affect your accuracy, but not with skeletal extraction. Also, you can start looking maybe for anomalies in the way that somebody moves. Are they showing some fatigue? Are they maybe favoring one side over the other? So I had mentioned before that you can look at the position of somebody's nose. You can also look at the position of all of these other things. This is what we're detecting using OpenPose. It's called Body 25. There's a couple other options that you could use if you were interested in specifically different points or configurations. This is the one that I used. And so here is the only part that gets somewhat technical, I promise, in case anyone is listening is super interested in the machine learning model that was used. It was a convolutional LSTM. All of the code was using the Keras machine learning library. And the reason we chose a convolutional LSTM is because convolutions will tell you about the spatial relations. So for instance, at any given frame of the video, how is this player's left knee relating to their right elbow. But the LSTM will tell you about the temporal relations. So how does the frame at position X relate to the frame at position X plus 5? So in other words, how does your movement at one given minute relate to your movement a couple of minutes later? So you put those together, you get the spatiotemporal relations that we're looking for. So not just what does your body look like at any given moment, but how does that relate to a couple minutes in the future and a couple minutes in the past. So these are the videos we're going to be looking at. You have Nadal versus Del Potro at Wimbledon 2018, Nadal versus Djokovic at Wimbledon 2018, and Nadal versus Djokovic at US Open 2013, 5 years previously. And you can see that the single constant here is Nadal, which makes it easy to follow for what we're doing, which is player identification. We've got that constant going through all of them. So starting with Nadal versus Del Potro, I used the Google Cloud AutoML video as a comparison to the baseline for just using the skeletal key points. So this is what, this picture over here is what the Google Cloud AutoML video sees. This is the input that it accepts, and it uses everything that you see here. So it uses even just the position of the player's shadow might be relevant at a certain time versus another, because the sun moves over the course of a 3-hour tennis match. And of course, coloring and the position of the camera and all of these different things, even whether or not somebody's tennis racket or bag might be present versus not present on the right-hand side of the screen where you can see the stuff might give it clues as to who's playing at this given moment. On the other hand, what we're feeding into OpenPose, or rather getting out of OpenPose, that's it. That's the only thing that our model is seeing. And as you can see, it is surprisingly accurate based on those key points alone. 88.6% accuracy versus this model, which again, not to detract from the Google Cloud AutoML, but is at 94% accuracy using all of these other clues. Obviously then when you combine these, and you can use confidence ratings, they make for a really good model. The OpenPose model actually does help boost that overall accuracy when used in conjunction with the object recognition. And I think I want to really hammer home how impressed I was with the Google AutoML, because when you're actually looking at the difference between Nadal and Del Potro from the back, it's tricky. And I chose that video specifically because I thought it was going to trip up the Google model, and it did not. So kudos to you guys. The other thing we want to look at is, okay, so we can look at within a match, can we identify these players? Sure. But what if we want to train on that match? So we're only going to show our skeletal key point based model, the information from the Nadal versus Del Potro match that we just saw, where the accuracy was 88.6%. And then what we're going to do is actually try to test it on a match that does not have Del Potro at all. And you can see the accuracy is still fairly high, but that just seems to be because it learned the model of Nadal so well. And this is a really good example. I liked this one because the accuracy on the match we trained on Nadal's all right. It's 83.5% precision when it's trying to figure out whether or not this is Nadal. So that means, more or less when it guessed Nadal, it was about 83.5% correct. On the other hand, it really knew Del Potro. It got very familiar with Del Potro. When it guessed that it was Del Potro, most of the time it really, really was. So now we present it this video. It's only ever learned these two players. It still stays roughly in line with its Nadal guessing, but now it knows that something's really up with this other person on the field. This is not something it's seen before. It's really throwing it off. It doesn't really know what to guess, and when it guesses, it's not doing well. Obviously, the only reason the accuracy is so high is because it's only dealing with two players, so there's only so poorly it can really do, but well above chance, which tells us that there is something that is really super unique about the way that these guys are playing tennis. Okay, so how about if we take the same players, Nadal versus Djokovic, and we've got an 85.5% accuracy. More or less all of the tennis that I tested on was approximately around there. Some were higher in the low 90s, some were lower in the low 80s, but that really converged around there for accuracy with just two players. We're going to test on 5 years previously. And you can see that it's still above chance. The accuracy is 62.1%, and those ratios stay roughly the same. Nadal drops from about 86% to about 60%, Djokovic 84 or 85% to about 64%, but still it's not at just guessing. So there is something that stays consistent between the way that these players are playing, even 5 years previously, on a totally different court, totally different camera angle, the whole 9 yards. Now, you might be saying, well, it's not really all that much above chance, but here's Serena Williams versus, I can't remember her first name, I'm sorry, Georgie. And you can see what happens when we actually try to figure out who these, like if you train on Nadal versus Djokovic and then you say, okay, tell me who's Nadal in this match, tell me who's Djokovic in this match, the algorithm just has no idea. It's just randomly guessing. It's not doing well. It thinks that maybe, I assigned Serena Williams to be Nadal, randomly assigned Georgie to be Djokovic by default, and it just has no idea what it's doing. So that makes this result much more salient. So what have we learned here, really? We've learned that there is something unique about your pose as an athlete. We have learned that we can maybe identify athletes from pose alone, but we can certainly identify athletes when you combine pose extraction with traditional object detection mechanisms that make it much more accurate to the extent that you could conceivably use it in a production setting. So now if you're a soccer team who has massive amounts of video, you've got all of these players in the video, and you're maybe outsourcing the player tracking for your games, you could instead consider automating that part of the pipeline. You can also then, once you have the pose, start associating it with things like, well, when this player approaches so you can remember Ramsey's setup where you're watching a player approach taking a shot at goal, you can take that skeleton that's being extracted and say, okay, what can we learn about this player's approach that influences whether or not he's making that shot that he's going for? You can also do things like try to make recommendations then, not just for these players, but imagine training a model on Tiger Woods and then using that to help other people correct their form so that they can actually drive more like Tiger Woods. You can also think of things like yoga, even practicing in your own home if you were to train a model on the way that professional yogis work, and then you offer the ability through a webcam to pick up somebody's pose, just extract it on the spot and tell them whether or not they need to correct how well they're doing now versus 5 months ago. You can also obviously start correlating to any qualitative or quantitative metrics that you might have for different points in these games or matches, videos. And that could be anything from serve speed to your score in figure skating. So you can start with quantitative, you can move to qualitative and see how it works. And of course, the reference I made to tracking a change in pose over time, trying to find anomalies, like does your pose change? If you have a player, you've been watching him for X number of games, you're pretty good at being able to identify his pose, and then all of a sudden it starts looking very different. You can flag that and say, is this guy potentially leaning towards injury? And I've been told that that can be a problem, because often players will want to play regardless of whether or not they might be feeling like they shouldn't. They don't want to tell their coach to bench them. So here, this gives the coach the option to say, you know what, maybe you shouldn't be playing because we're showing that you're favoring your right side, and is that actually bothering you, and confront it up front. So more research needs to be done in that direction, which is something that we're dabbling a little bit with now. But that is one of the potential directions we're taking it. Another that I referenced earlier is possibly looking at things like, apparently I've been told that players who look around the field more before they pass are actually objectively better in certain metrics than other players. So what if you're recruiting as a coach and you want to be able to identify players who do this? Well, really, of course, eyes move independently from the nose, but often the direction that the nose is pointing is a really good proxy for gaze. If we know which direction a player's nose is pointing at any given time, can we then look to find out which potential up-and-coming players look around the field most before passing and flag them? So hopefully this has been interesting to you guys, and I'm happy to take any questions anyone might have.
No questions? All right. Well, thanks again, Katherine.